In this video, I'm going to complete what we were doing in section 4.5, where we were looking at applications of exponential functions. So here it talks about, actually we were pretty close, we had just a couple of problems left to do. Here it says exponential growth and decay models. We're going to focus on exponential growth. If k is, well actually the formula is there, it's a equals a naught times e to the kt power. So it looks like a sub 0, we say a naught. I don't know why, but that's how we say that. If k is greater than 0, the function models the amount or size of a growing entity. So a naught is the original amount or the size of the growing entity at time 0. So we're just going to say the original amount at time t equals 0. A is the time, or I'm sorry, the amount at time t, and k is a constant representing the growth rate. So those are the different parts of the formula that you need to know. Now if you look at this formula closely, a equals a naught times e to the kt power, it looks a lot like PERT, or PERT formula. In the PERT formula, P was the starting amount that we put in a bank. Here, it's just the original amount, or like it might be the number of bacteria at the beginning, or the initial amount. And then R is a rate of growth, whereas in the PERT formula, it was a percentage rate, which basically described the rate of the growth of money, of your money. And then T was for time in years normally. With these problems, a lot of times T may not be years. So it's very similar to PERT, just a little bit different. So let's go ahead and finish these last couple of problems. So in number 5, it says the number of bacteria, N of T, present in a culture at time T, T's in days, is given by N of T equals 90 times e to the 0.05 t power. So I'm going to go ahead and write the basic formula for growth. And we know a naught, or the number in front of e, is our initial quantity or the beginning quantity. And so here it says on part A, what is the initial number of bacteria? At time 0, that would be 90. So we're starting with 90 bacteria. What's the growth rate? That's our k value, which is 0.05. And we normally write that as a percent, so 5%. Move the decimal 2 to the right. How many bacteria are present after 5 days? Well, 5 is the number of days, that's our t. So we're really just finding N of 5. And so we'll plug 5 into the formula. And you ought to be able to put this into your calculator, and you should get 115.6. Now, if we were talking about people, we wouldn't round to the nearest decimal. We would round to the nearest person. Kind of the same thing here. I'm going to just write this as, let's go ahead and write this as 116, and that would be bacteria. All right, I don't know, can you have 0.6 tenths or 6 tenths of a bacteria? I don't know, maybe you can. Let's look at D. So it says, when will the population of bacteria reach 140? So we have an initial amount of 90, and we want to find out how long it takes for the population, or at what time the population is going to be at 140. So basically, they're giving us, actually, you know what, I want to mention one other thing here. When we say the word when will the population reach 140, what they're asking for is time here. How much time is it going to take? What's t going to be? All right, so we said 140 is actually going to be what 90 bacteria grow into, and so that's going to be our N of T. And so let's go ahead and plug these numbers in. So 140 equals 90 times e to the 0.05t. So we knew the initial amount, we knew a, and we're looking for t. So let's go ahead and let's see. We want to. The thing is, this is almost in exponential form, where we have the three parts of an exponential equation. The only thing is we've got this extra number in here, 90. So if we divide by 90, we'll be able to get rid of that 90 there. So we'll divide by 90 on each side. We're going to get 1.556 is equal to e to the 0.05t power. You notice I've rounded this. I could have written this as 14/9, but I just took it 3 decimal places. That should be good enough to get a good final answer. Let's go ahead and change this to, now that it's an exponential form, we have a base of e, an exponent of 0.05t, and an answer of 1.556. Let's rewrite this so that it's in logarithmic form. So you should get natural log of 1.556 is equal to 0.05t. So again, the base here is e. We don't write the base for a natural log, we just use the ln. So in this problem, if we're going to solve for t, we need to get rid of the 0.05 by dividing. And actually, I could be putting 14/9 or 140/90 in here if I wanted to get a little more accurate answer. Accuracy always depends on the person and how much accuracy you need in any particular situation. We're going to just use the decimal value here, but we could have used 14/9. Let's go ahead and divide by 0.05 on each side. And so if you throw that into your calculator, you should get about 8.8. All right, so that's 8.8. Let's see, this was days, or almost 9 days. It's really pretty close. Either of those answers is fine. Let's go ahead and move on to our last example. So basically number 6 is just like the one I just did. And so you'll just do that one, and then we're going to go ahead and skip to oh, I'm sorry, I forgot one problem, part E. It says, how long will it take for the number of bacteria to double? Well, let's see. Here's our formula. Our starting amount or initial amount is 90. Well, if it's going to double, that means n of t is going to be 180. So let's go ahead and plug 180 in here. And so now we need to solve for t. So this problem now is a lot like the one we just did. We're going to need to divide each side by 90. And so now we have the three parts. This is the form of an exponential equation where we have base, exponent, and answer. Let's go ahead and switch this to the logarithmic form. So go ahead and do that, and then you might want to stop the video, and then you can see what I got. All right, so you should get natural log of 2 is equal to 0.05t. If you said log base e of 2, that's the same, but we would rewrite it as natural log of 2. So we're going to need to divide by 0.05. And notice I put parentheses around the 2. When you put it into your calculator, you want to put it in just like it looks there, natural log of 2 with parentheses around it, divide 0.05, and you should get about 13.9. So I'd say that's pretty close to 14 days. All right, let's move on to our last example. So again, you're doing number 6. I'll do 7 for you, and then you're going to need to do number 8. So basically in this assignment, you're just filling in and doing the problems that we didn't do in class, or I didn't do here in the video. Number 7 says the number n of t of bacteria in a culture, so n of t is the number of bacteria, is modeled by this function n of t equals 250 times e to the kt power, where t is the time in hours. So t is in hours. If the number of bacteria in the culture is 280 after 10 hours, find k to 4 decimal places. All right, so it looks like we're finding k here. So 280, that's going to be our n of t, or the number of bacteria. That's what we want 250 to grow to, and we're going to figure out what k is if we're at 280 after 10 hours. So 10 hours, that's going to be our t. So let's go ahead and plug our numbers in. Excuse me. I'm going to rewrite this so that you have the 10 before the k. So now we're solving an equation very similar to what we did in the last couple of problems. We've got too many parts here. We've got to get rid of that 250. So we'll divide each side by 250. So 280 divide 250, we're going to get 1.12 is equal to e to the 10k power. So now we have 3 parts, base, exponent, answer. We can go ahead and rewrite this as a logarithm. Natural log of 1.12 is equal to 10k. We need to solve for k, so let's divide by 10 on each side. And if you put that expression into your calculator, you should get 0.0113. And that's our final answer. And that's the end of this video.